tutorial over Lab 6, Dijkstra's shortest path for Dr. Rizk's class, Data Structures 2430. So today we're just going to go ahead and look at the instructions briefly and kind of read over them, and I'm just going to go a little bit into which parts are going to be things that we need to focus on, important parts, and really just kind of how to understand what we need to do and break it down and actually put it into code. So the first thing that we're going to go ahead and look at is this is going to be over graphs. A graph is denoted as G equals VE, which is vertex 1 to vertex 2, which is going to indicate an edge between two vertices. This edge is going to be weighted, which it says further down here. And we're going to try and find the shortest path from one source point to an endpoint. And I'm going to use Dijkstra's algorithm because the lab is over Dijkstra's algorithm, but there are other ones that you could use if you wanted to. So the input files are going to look a little bit similar to what we see down here. And we're going to have on the first line m, n, x, and y. M is going to be the number of vertices in the total input, and it's going to be the number of edges in the graph, and x is going to be our source, and y is going to be our destination. After that, each line is going to contain integers a, b, and c. A is the source, b is the endpoint, and c is going to be the weight of the edge between the two vertices. So 1 to 2 has a weight of 5. So I'm going to go ahead and start by saying how we're going to go ahead and get this file inside of our program so that we know how we kind of want to pass in each integer into our code later on. So this is going to be how we read in the file. First, we have to pass in the necessary arguments to initialize our if stream operator, and then I also initialized a few variables that we can use later on. Like earlier in the instructions, there is the 4 variables that we have to read in, right? And so everything is kind of as it seems, and then for the purposes of reading in our stuff, I'm going to have 1, 2, and weight. So 1 is going to be vertex A, vertex B, and then the weight between the two. And then test isn't really used. I was using that while I was writing the code to make sure everything would pass through the correct amount of times during the while loop. So to actually use the Dxtr algorithm, I'm going to go ahead and store everything into an adjacency matrix. You have another option to use if you don't want to use an adjacency matrix. You can also use an adjacency list, which is essentially the same concept, just a different container. I'm going to fill it up with zeros so that it's initialized and no part of it is empty so that I don't get a segmentation error. It's important that you do this because if you don't fill up your adjacency list or your adjacency matrix before starting to pass things into it, you might get a segmentation error if you don't fill it up. I had to learn this the hard way, so just go ahead and initialize everything with zeros, and you can go ahead and add everything in as you go, and that way that is less likely to give you segmentation error later in the code. So next I'm going to extract the data from the file. I'm going to keep these as separate from these variables up here because I'm going to need to use those for later. I'm going to keep those stored away in there. Alright, so next I have my while loop, and this is where 1 and 2 are going to come into play. So we have vertex 1 and we have vertex 2, and then we have the weight between them yet again. I'm going to go ahead and fill up my adjacency matrix with the actual values aside from the 0. I went ahead and put this if statement in here to prevent from overwriting if there is a problem with the input file, so that none of my vertices that were already in there get overwritten in any way. So let me go ahead and explain this part right here. Since this is an undirected graph, that means that we need to have the vertices going both ways. So in the input file, we are given 1, 2, and 5, correct? 1 to 2 is the direction, essentially. So you're going from 1 to 2, and the cost of that traveling is going to be 5 units, or whatever. The cost is going to be 5. And the same thing for here, 1 to 3, and the COSC is going to be 3 again. If we were to just enter in these values like this, without flipping vertex A and vertex B, we would have a directed graph. And that means that it can only travel in one direction. However, for this assignment, we're going to want it to be undirected so that we can travel from 1 to 2, but also from 2 to 1, using that same path that costs 5, and the same thing for 3 to 1 and 1 to 3, costing 3, and so on and so forth. So that is the reason why we switched the two indexes right here. We have 1 to 2 and 2 to 1, and they both equal the same weight because they are the same path, just reversed. And after that, we're going to have the Dijkstra function call, but I have to go ahead and write that first. So one of the main things that allows the Dxtr algorithm to work is a little mini function that kind of works in tandem with it that finds the minimum index of whichever section. If we were to break down the adjacency matrix, we would have rows and columns. So it's important to know the order in which you can iterate through an adjacency matrix. So they are all arrays. It's an array full of arrays. So on the outer loop let me scroll down here. So on the outer loop of the adjacency matrix, we're going to be iterating through the columns. So that means that's going to be the vertical iteration from the top 0 to the bottom 5 or whatever, however full it's going to be. And then on the inner loop, we're going to be iterating through the rows. So for whichever index we are in the column, say 0 or 1, we'd be going horizontal to that index so that we are going to get every other number that is stored inside of that array. So here is the function that kind of works in tandem with the Dxtr algorithm, or I guess function. So you're going to pass in an integer array, a Boolean array, and a size. So inside of the distance array is going to be the distance for each vertex, or away from the source vertex. Our minimum is going to be established as a very large integer. I didn't want to use int max for this because I find that it is a little bit messy, so I just kind of initialized it as a 99, so almost a million. Anyways, we initialize our two values up here, and then we want to iterate through our row, essentially, that we're at. It's going to give us the column index, then we're going to iterate through that row to get every vertex inside of there and see that has been traveled, which is going to be this Boolean array. It's going to keep track of each vertex that we've already traversed and kind of accounted for so that we can exit accordingly. Okay, so it's going to return the minimum index. All right, so I do have one more little other helper function that kind of goes in tandem with the Dxtr algorithm before I write it, and it's going to be the print function. Quite simple. So the Dxtr algorithm that we are going to write here in a minute is going to give us, like I said, the shortest path from the source node to every other node inside of the graph that is connected to it. For this lab, we only really need to focus on one source and one destination. So it's nice that we're able to get every length for every destination, but we only want the destination that is being asked for inside of our input. So here we have source 3 to destination 7. So we want to find the shortest path from 3 to 7. 3 would go here and 7 would go here. So of course we have to pass in our distance array because that's where we're keeping the sum of every distance away from that source node. And we also have to pass in our out file print because we do need to print this to a file. But yeah, so we're going to want to iterate through it until we find the index that we're looking for, the destination that we want, our endpoint, and then we're going to go ahead and print out that distance because inside of that index is going to be the distance away from the source node to this node. Alright, so last but surely not least, the most important part of our homework is going to be, or I guess lab, is It's going to be the Dijkstra algorithm itself. So I want to start with kind of the things that we're going to pass into it. Of course, we're going to pass in our graph, and I have initialized it as 10, 10 inside of the main as well, because these adjacency matrices can be a little tricky sometimes. And then, of course, we've got our source, and then we've got the size of our graph, and then we've got our destination and our out file print. So here is where we initialize our distance array and our Boolean trace array. The Boolean trace array is very, very important. It's going to keep track of all of the vertices that we have already visited, so that way we can be as efficient as possible and not really, repeat too much. And then here we are initializing our arrays. So we're filling them up before we do anything to them. So right here we're going to initialize the source index. So that's going to be whatever index we're starting at. For input 1, it's going to be 3. So we're going to make sure that the source is 0 units or whatever away from itself, because it is itself. Down here, our outer for loop is going to be iterating through the columns of our adjacency matrix. And then we have amor. So amor is going to return us the minimum index, which is basically going to be the closest index to our source. And then we're going to go ahead and mark that one as true because we already traveled it. And then inside of our second for loop, we're going to go ahead and iterate through our rows now. These if statements, I kind of broke them up because they're quite large, but in order to be added to the distance array, all of these parameters must be satisfied. The trace array must exist, the graph must exist, and the distance cannot be equal to infinity, which is kind of what the 99999 represents as infinity. And it also needs to be less than the distance that's already there. And so that way you can go ahead and add that total distance inside of the distance array. And then out here we have our print function, and as I went over that a little bit earlier, that's going to give us the distance away from our source to endpoint, the total distance, the shortest distance. I'd actually like to kind of repeat this one more time, but for this lab specifically, I think it's very important to know like where you're starting from, and I believe this lab doesn't really specify that they're not starting at 0, that they're always going to be starting at 1, but just kind of like pay attention to that, because you are going to need to start off at the index 1 because index 0 does not exist. And so you want to iterate correctly, and that's why you kind of add 1 to the size so that it makes sure to get every single index, because you're going to want to be equal. I mean, you could either do the +1 or you could do less than or equal to, right? It's really up to you. Anyways, I've called the Dijkstra function right here in the main, and I'm going to kind of go over like what I called in. And so we have our graph, of course, our source node, the size, which is going to be the total number of vertices given to us in the first line up here. Then we're going to have our destination, which is also given to us in our first line, along with the source. And then, of course, we're going to pass in our out file print. So I'm going to go ahead and run it. And so there we go. We get 15, which is perfect because we are using input 1, and so answer 1 is also 15, which is quite nice. And then we can go ahead and do input 2 as well. 4, perfect, there's 4. And then we can go ahead and do 3 as well, which is going to give us 6, and that is exactly what we needed for the output for answer 3. So this is basically it, and then of course you can call in your argument manager stuff. Alright, and so that works, and so now we can kind of run it like this. And passes all of our stuff, and we can see it properly prints out to the output file correctly, which is exactly what we need. So I'm actually going to go ahead and kind of explain the graph with a little bit more of a visual. Kind of like a little segment that I'm going to do on this. So I went ahead and took the input file for Lab 6, and I kind of like made it into visual representation. So we have the vertices on the left, the two values on the left, and then we have the weight between each vertice. And this is kind of more of how it looks as we have the source to the endpoint, and then the weight is going to be the cost that it takes to get between each edge. So here I kind of just started off at 1, and then I just kind of drew it how it goes. Just kind of a way to visualize this, I suppose, would be that you have your source index, right? So for input 1, our source is 3. And our destination is 7. So it has to get all the way over here, and it has to use the shortest path possible. So what the Dijkstra algorithm basically does is it tries every single path from 3 all the way through the whole graph to 7. I'm sure that it doesn't go to 6 at all because it's just out of the way. But it tries every path and then it returns to you the shortest path. The two really options that you have is you can go 3, 1, 2, 5, 7 or 3, 1, 4, 5, 7. But this edge costs significantly more, and so does this one, so it's going to favor, it has to cross to the 1 in order to get to the rest of the graph, so it's going to have to go through this, and then compares 5 to 6, 5 is less, so it's going to go to 2, and then it's going to go to 5, which is really like the only other option, right? And that's going to give us 15. So I hope this was a pretty good explanation and visualization.